No, it's fine. I was kind of hoping you'd go over, that way I would cut down this one. Okay, this is sort of like a Perl talk, but you're not going to see much Perl code in it because I'm mostly going to talk about the math. I got distracted by a problem and ended up doing all sorts of different things with this. There's this thing called excellent numbers that I found about through Mark Jason Dominus. If you read his blog, The Universal Discourse, he often presents these number theory or weird algebra problems and sometimes ties them to programming. And I'll explain the problem in a minute. But basically, he wanted to ask how much of the number space can we look at with a computer to verify that this thing is true. And he does some back of the envelope calculation and he comes up with this thing that says to get to this size, it's going to take more than 1 trillion years of computing time. And I thought, okay, that seems like a fun problem. Let's work on that. Because I'm also really interested in benchmarking and profiling sort of things. Those are major parts of my book, Mastering Perl, because I used to be a scientist, and the job of a scientist is to make graphs. Now, you don't think that's true because they don't tell you what your life's actually going to be like when you get a job doing the thing you study in school. But that's what it is. You make graphs. And what you need to do is make the line go a certain way. So here's the problem. If we can take a number that has the digits that have a front part and a back part, which we'll call AB, so don't think of that as multiplication, just think of that as two halves of numbers looking at it as a string. If you take the back half and you square it and you subtract the front half squared, you get back the number that you started with. So for instance, if you take 48 and then you make 4 of the front half, so we'll call that A, and 8 is the back half, so we'll call that B, square those, and then you know what you're going to get, 64 minus 36, and that gives you back 48. So we'll say, given this definition, that 48 is excellent.
Actual mistake there. 16. It's 16, not 36.
Oh, 16, okay. That's fine. So that works out. Okay, so same thing with this. So we have 34 and 68, those are our A and B. We take the squares of those, we take that, and I think that's probably right over there. And we get back this number. So, there's also an interesting pattern, which I'm not going to cover here, but it's on the website, that we have 48, and we have another 48 in here. They just happen to be at the end of these numbers. If I take any numbers of 3s and the same number of 6s, that number is also going to be excellent. So 33, 4, and 66, 8 altogether. That's excellent. And that pattern continues ad infinitum. And I proved that that's an infinite pattern, so there's also an infinite number of these excellent numbers. That's just one of the interesting patterns. So what I want to do is go through a bunch of numbers and see what this does. So we can do the brute force sort of thing. Now, don't worry so much about what's going on here. The basic part is there's a for loop. It's going from some minimum up to a maximum, and then it checks the next number, and it goes through some stuff to do that transformation I just showed you. I split it up into a back half and a front half. I do the squares, I do the subtraction, I compare it to the original thing. You can do that, and that's the first way that everyone does it, and if you go and you look at the various things in Rosetta Stone or something like that, the Python people, Ruby people, everyone is doing this sort of thing. Because that's what you can do when you're taking your first Python class in college and they give you this problem to work on. You just go through and you do that, and then you get to the point where you say, okay, I've gotten bored of this, my computer ran overnight and I got this far, that's as far as you can get, and then I'm just not interested in the problem anymore. But no, this is where the problem is just being interesting. And if we did it like this, Mark Jason would be right. It would take 1 trillion years to get to a certain number of digits. But what I want to do is I want to figure out something like, what are the first 1 million excellent numbers? I just pulled that out of the sky. And we've done that by now. And the way that you can do that takes about 3 hours, when I'll show you that way at the end. And so the stuff that Mark was calculating was completely based on something that we wouldn't want to do anyway. Which is always the problem when we want to make things faster. We're trying to make it faster based on the same thing we keep doing. Let's make the Perl faster, we'll make the hardware faster, we'll do something else. The way to make something faster is to come up with a much better way of doing things. So here is, for my little laptop up here, this MacBook Air that I bought 3 or 4 years ago. This is about the time it takes to get up to about 8 digits, go through all the 8-digit numbers. So that would take 100 seconds there. So that's pretty quick. You get, but to keep going, that line just goes up and up and up. This is what we're doing. We're just checking that number, then we're checking that number, then we're checking that number, and we keep doing that, but that's no good. If we look at this, we go back to this definition, let's break that up. What we actually have here, if we write this out so it's an addition, we got a times some power of 10, k being the number of digits in b. We shift that over, we add that to b, we have that. We'll rearrange a little bit. So we got all the b's on this side and all the a's on that side. And now what we can do is this. We know what our a is, so we can just plug it in there, and we can see if we get something that satisfies this. But for numbers that get big enough, b squared minus b might as well just be b squared. So we can see if we get something that's close to a square. Maybe we have to check a little bit on either side of that, but we don't have to check every number. We just have to check all of the a's before we are going through and checking a, b, a, b, a, b, b. Now we can just go through the a's. So instead of checking 10 times 2 to the k, we're checking 10k numbers. We have reduced the space by the square root of what we were doing before. That is a big leap, and that's not something anyone considered. So this rules out almost everything we were checking before. Okay, and this is just a code that does this. We have a start A and an end A. We take that, we plug that back into the formula, we get some square root of that, and we're just going to take the int of that. And then down here is a little bit of stuff to say, did I get close to something that's a square root? I'm going to try on either side of it, because maybe that b squared minus b has a little bit of an effect. And if I get something there, I say, okay, I found the thing, and I just print it out down here. Just say $a and the root, because the root is b. And so now we get something that looks like this. In about the same time, I can get up to 18-digit numbers. This is 100 seconds. This is something where you're not going to get bored sitting at the keyboard. You're not going to have to wait a long time to get the next thing. Okay. Again, this is what I did when I was a scientist. I just made graphs. And if you make graphs that do this sort of thing, where you show that this one moves over, or that one moves up, or something like that, everyone's very happy. The trick, by the way, in any sort of that stuff is to make graphs that show the thing, the political point that you want to push on people. Okay? Even if it's true, you're trying to get other people to do something by the picture that you're showing them. Okay, now here's all those numbers. So there's 48, there's the 3648. Look down here, there's the 3334, 6668, and then there's with 4 3s and 4 6s. And we get some other interesting patterns. 3468, 3468, 3468. An odd number of repetitions of an excellent number next to each other is also excellent, and I proved that. And so we have another infinite set of excellent numbers that do that. And look at this. 48, 48, 48, 48, 48, so on and so on. Mark Jason looked at this a lot. He proved that any combination of 48s next to each other are going to be excellent. But that's really just a special case of the 3468 thing. It's just ones with the 0 3s and 0 6s. A lot of the interesting things I got out of this when I'm doing all these improvements and generating numbers that people haven't gotten to before is I can see long-range patterns that no one cared to look at because they solve such a small part of the space. Now, once we got a bunch of numbers like this, we can see patterns that can improve our program even more. So let's just put the lines down where the A's and the B's are, and look at that for a minute, if you can see that clearly, and see if you see a pattern in the A's. Anyone want to guess?
It's about twice.
It's about twice?
Some of them.
Some of them.
Yeah.
There are no A's where the first digit is bigger than 5.
Good, that's a good one. And we're going to come up on that. There's another one that's really interesting here. All the A's end in 0, 4, or 6. And you've got one, so far we have not seen an A that starts with something larger than 5. Okay? So, now we're going to prove that we only have to check the A's that look at 0, 4, or 6. Which means that we can get rid of all the ones where it's 1, or 2, or 3, or 5, or 7, and all this other stuff. So let's go back to this. Now let's do this all mod 10. So the arithmetic is still going to be the same even though we keep taking the remainders after division by 10. So we can get rid of this guy because that's just the power of 10. That's always going to be 0. So in mod 10, this difference here, the b squared minus b, has to be the same as a squared, which means that a squared has to end in one of these things because the squares have to end in one of those. So if we look at the things where b squared minus b and a squared line up, mod 10, we'll just try them all. So the 0 will work because if the b is 0, mod 10, it will match the a, but the 1 won't work, or excuse me, the 1 will work, the 2 won't work, and so on. And you can see how it works out there. So, if we look at that, a squared being the a times the a, and the a has to be one of those, 0 over 6, then the a has to be one of those. So we've proven that. So we can skip all the other a's for that stuff. So we rule out another 2/3. We got rid of 66% of it, then we got rid of a bunch of more of it, and now we've gotten rid of a bunch more. So we'll just put a thing up there that says next unless it ends in one of those things. That's not a great way to do it. If I really wanted to do this, I would not do a regular expression and look at the last character and all that sort of stuff. I would just generate the numbers so that it gets me to the next one without having to do that. You have to add the right amount to the thing so it gets to the next number. But that's easy. And why make things harder right away when you can just put that in there, let that run, and then you can go work on your stuff somewhere else. Another great thing to think about when you're trying to make a program faster, does the time I'm going to need to make this a lot faster take longer than it would for the slow version of the thing to complete? Because if you tell me as your team leader that, yeah, just give me a month and this thing will be done, but the sales guy needs it tomorrow, I don't care how good you are or how pretty the program is in a month because we needed it yesterday. And I've had things like this, and I think Abigail gave a really great talk on this that a lot of people reacted sort of surprisingly to, where if you need to make a bunch of money, who cares how pretty the program is? The point of the work is not to make pretty programs, the point is to make money. And so sometimes you have to make ugly stuff. And I make plenty of ugly stuff because someone comes to me and says, this thing is costing us $10,000 an hour. I said, I can't look at it all right now, but I can put this hack in and then we can wait. So that's that sort of thing. So, let's go back to this. Now let's try to figure out a maximum A. So we don't want to go through all the A's. So we notice this thing where we didn't see an A that has a value that starts with a 6 yet. So if I take the maximum B's, which I just are all 9s, and I do the math, I'm not going to show all that here, A turns out to be about this number. 6.18 and then a whole bunch more digits times whatever that power of 10 is for that number, K being the number of half digits and the big number. Does anyone recognize that number? It's what?
Tau is 2 pi.
Maybe in the alternate universes.
It can't be, it's
6 points.
algebraic number, so it can't be something with pi.
That is the,
Okay, the limit could be, but I don't think it should be pi.
you put that together with the maximum B and you get the golden ratio. And I have not figured out how to prove this yet. Because it's not the golden ratio, this is just the maximum A. The maximum excellent number is not going to be the one with the maximum A in all the cases. So the limit for the maximum A approaches the golden ratio as you get bigger and bigger numbers. And we actually are going to see numbers that begin with a 6 later on, but never ones that get bigger than 6.18 something. But to do that, to find that, you have to have something much, much faster that's doing something much, much different, to get way beyond what the brute force case is doing. And most people never get to this point where they can even think about this stuff, because if it doesn't run overnight and they turn in their homework assignment when they're done, they never get to find out these wonderful things. And this is sort of the thing that I wish computer science programs would do, even though computer science programs aren't for making programmers, was give them some sort of long-term project where it just seems impossible and they just have to deal with it. They have to come up with something. It's not this directed thing like you have to use this Java feature, okay, you use that Java feature, you get marked. I was like, no, you have to go struggle with this problem. And maybe we don't know what the answer is, but that's what work is, right? We don't know what the answer is. Okay, so we can rule out another 40% of that stuff. That's the trick what we're doing so far. How much stuff can we just decide right away that we don't even have to look at? Okay, and that means I have to start using big nu. Because in Perl, I'm getting to a point where the numbers are large enough that it can't do the integer math. Okay, so this is the same thing. And this runs, it takes a long, long time, but it's spitting out numbers. And since I don't do this, I'm not getting paid to do this, I can just put it on a couple of processors and let it run and do its thing and look back a week later. And I'm getting a bunch more numbers out of this. The big nu takes about as long, when you get to the bigger numbers here, it just starts up a little bit slower. Okay. But in Perl, the big nu is really just a minimal interface to GMP, the GNU library for this, for the big numbers. And I went to look at adding more stuff in, because it's very easy. You see that they've made an interface to one of the functions in GMP, so you just sort of can cut and paste and change the functions and move some arguments around. But then I was like, that seems like a lot of work. Why don't I just write this in C and use GMP? It would probably be faster to go back and patch it in Perl, because GMP and C is a lot of, I have to set up this data structure and I have to do it exactly right, and if I don't, you don't even compile. So then I had to use Valgrind for a while to figure out why GMP wasn't doing this thing, because I'm an idiot. And honestly, there was a thing, I think, I looked at the maintainer for this, and this is just my impression. The person I had to send the patch to, I was like, no, just not going to do it. I don't need that hassle. I'm not going to argue with this person to get this patch in. Or it might have been a subsidiary module of this. But curiously, as we've gotten to some sort of entrenched things in Perl, there are a lot of clients I have who just have a list of people that, if they work on the module, they're just not going to use that module. Because they don't want to have to get berated online for some patch they send in. Okay, so I do it in pure C. And notice now, for the same amount of time, I'm getting up to about 20-digit numbers. Not so bad. I prototyped something in Perl, I got a lot of the way, I discovered a bunch of stuff, I dropped down to C when I needed more speed, but it's not giving me that much of an improvement. It's not like astronomical. It's just a little bit, and I know that this isn't going to last forever. It has the same curve, so it's just shifted a little bit, but it's going to get as tough as it would in Perl as I go on. It's just a little bit faster, just a tiny bit faster. And then this happens. I was writing about this in blogs.perl.org, and Joel Berger, who works at Server Central, and Doug Bell works there now too. I think they showed this to their boss, and he writes to me and says, hey, we have this 80-core machine that's laying around that we let open source people play with. One of the implementers of ZHS likes to test things, and they sponsor this, and so they give him this machine, he goes and he tests this thing, and then for 29 days out of the month, the thing just sits there. So I said, okay, yeah, I can use that. Now the thing is, I have a C program that's going to check these things. Now I have an 80-core machine. I don't want to write any stuff that has concurrency. I don't want to write anything where one program says, oh, I got 80 cores. So what I'll do is I'll just have a Perl program that starts a C program that says, look from here to here, and it's just a single processor thing. And then I'll start some other single processor thing. One of the things I often see Perl people doing is going towards these great asynchronous programming things for things that are actually independent, that they don't need to coordinate with each other. And I'm saying, you've got Unix, it's a multitasking thing, you don't need to build another multitasking layer on top of that. So I'll just do that. And then this is a great part. So all these C programs are outputting stuff. This is where I am, this is where I am, this is where I am. Because these things start to get really sparse, and we're looking at things that are, say, 30-digit numbers. And the runtime, even over 80 cores, is something like 3 weeks. And if one of those fails, well, where was the last time I did something? I don't want to start over. So every 15 minutes or so, it's spitting out, this is the number I'm checking, this is the number I'm checking, this is the number I'm checking. So if one of those things fails, for instance, the machine goes down, or I get kicked off because the ZHS guy wants to come in, and use the machine because he gets priority. He just shuts down my stuff, it flushes some output messages, Perl comes back, reads the output, oh, okay, I know where to start on this run, I'll just go back and do that again. And so now I've got Perl running, and C running, and I'll have a few other things too. Oh, by the way, and it tweaks the number of funds. So I wrote about this, I think, for Perl tricks. Different ways of recording things off-site so you know where you got to. So yeah, I could set up Redis, I could set up a database or something. No, I'll just make a Twitter account, and I'll just post it to Twitter, and then this thing can read the Twitter account and see what it's found so far, and then know where to pick up.
What's the Twitter account?
It's at Excellent News. And actually, I think I've gotten to the point where I stopped running the program that tweets the stuff, as you'll see coming up, because we did something really fantastic. And the 140 character limit got in the way.
Create images.
But you
Yes.
can use
Or
different
link.
encoding. Sorry.
Is that saying it?
You can use a different encoding, like base 36 instead of base 10.
Yeah, I could do, there's all sorts of things I could do.
Go-
But this part became uninteresting after a while, because there's someone who comes to the party who just destroys all the work that we did. Okay, now this is really interesting. So I get to work with Sinon quite a bit. He's a really good C programmer. And I've been doing all this GMP stuff. And if you've ever used GMP, or the Perl version of it, the reason that it's slow is that it makes all these structs and then passes these things around, and then it has to undo the structs and then stringify the stuff to show you something. Okay? That's why the Perl version is slow, because then it has to take the Perl stuff, translate it to the GMP stuff, which translates it into its internal stuff and does a bunch of crap and brings it all back. There's actually a way to use 128-bit ints on 64-bit hardware if your compiler supports it. Okay? So, and it's really, really fast, and we don't have to make structures, we don't have to do any of this other stuff, it's just going to do this. And there's also a way to do 256 bits. And then we spent a lot of time reading papers about how to do large math with 64 bits. You do this part of the problem, you do this part of the problem, and there's so many multiplications you have to do, and you add it all back together in certain ways, and it all works out. The sort of stuff that you would expect to get out of something like reading the art of computer programming, the GNU stuff, where you have to split up the problem into various sections and make sure you carry this byte over to this section and that sort of stuff. But no more GMP, so this got really fast. And I don't think I have a graph for that. By the way, as I'm doing all this stuff, and before I get to the final thing that I actually did, I'm trying this in other languages. For instance, I went to the Julia language, which is supposed to be really good at math stuff. I don't really know what their goal is, because it seems not to be anything different than what's already out there, except that they wrote it. And I tried it, and I posted this thing to Stack Overflow, and I'm glad I get to do this sort of thing, because I get to see what it's like to have everyone think you're an idiot. Because outside of Perl, no one knows who I am. And I post this thing, I tried this, and I had a complete working program, and it's not as fast as I thought it would be. What did I do wrong? And then they said, well, obviously you're just an idiot, and that's the thing that you did wrong, and that sort of stuff. And they went on, no, you have to use this. I'm like, well, where are the docs is at? So, well, it's not in the docs, you have to get it out of the Git repo. Thank God for Perl, most of our stuff is documented. I don't think I've ever answered a Perl question by saying, oh, you have to get it from Git. And then compile that and then run that, and it's just Perl 6, yes, you have to do that sometimes, because Larry likes to stay up late at night and things are different the next day. I tried this in Lisp and just gave up because the number of parentheses that I was having to track. But the Lisp was really interesting because it has big numbers built in. It turns out it's as slow as all the other things that use big numbers, though. It doesn't give any magic. It's the same hardware. You're not going to get anything more out of a different language. Well, I think someone said in a talk that the language is not the thing that usually matters in this. It's the stupid programming. Okay. Now, as Sinon and I were doing all this, we were very proud of ourselves to the point that we were actually working on 34-digit numbers, and we were going to finish that in about a month of 80 cores running continuously. That's a lot of time. I think on the webpage I have for this, excellentnews.com or whatever it is on the first slide. I did comparisons of actual computer time, and we're talking, 40 years or something like this, I think is what it turns out to be. Of actual CPU time, 40 years of CPU time to get this far. And then this other guy, Matthew Arcus, comes along. He's a Python programmer. And he realizes this sort of thing. Now, you probably recognize this sort of thing from high school algebra. There's the thing at the top that we started with. And then we're just going to rearrange it to get the A's on one side and the B's on the other. And let's just multiply everything by 4, because 4 is a nice number. That's nice. And then we're going to add 1 and subtract 1. But over here, we're going to add 10 to the 2k and subtract 10 to the 2k. And all of a sudden, we get this. We have a square here, we have a square there, and we just have this minus 1 and this minus 10 to the 2k. But then you rearrange this to get all the squares on one side. You've got this, 10 to the 2k minus 1, and let's just call that a and b. And then when you have something like that, a squared minus b squared, what you really have is a plus b times a minus b, which is a special sort of thing, because you can say this thing, we're going to call I, this thing we're going to call j, is going to be this thing. Now, I didn't really realize the importance of what this thing is. Well, that like word moves. But for mathematical people, especially number theory type people, that is a very special number. That is, and he's going to implement this in Python, but 10 to the 2k minus 1 is 9 times the summation of the powers of 10. So let's say that k is 0, you get 10 to the 0, which is 1. You get k is 1, you get 10, and 10 to the 1, which is 10, then plus 10 to the 0, which is 1, so you get 11. You get 1, 1, 1, and 1, 1, 1, 1, and so on, and all those are just multiplied by 9. Now, the curious thing is that these things here, forget the 9 part, I also always think I can cover up the thing that just projects on your hands. This part here is called a rep unit, a repeated unit, unit being 1. And there are all sorts of mathematics that have already been done in these things called rep units. They have taken these things and they have factored them to find all their prime factors. They've done this for rep units up to thousands of digits long. There are people who are interested in this sort of problem and just let their computers run. They have conferences about this sort of stuff, and they probably wear t-shirts and have hats. Which means if we go back to what Matthew came up with, we know this side, and we know this side already because people have already done that work. We just have to look it up. We know all the factors of this rep unit over here. Well, we have to have 2 factors of 3, right? Because we have a 9 in there. And so we just have to partition those factors, and then once we make that partition, we got an I and a j, we can go back, we can figure out what a and b is, which means we can figure out what these are. And so instead of going through the entire space of A, like I was doing, which I thought was really clever, especially since I could skip a bunch of things, he doesn't go through the entire space at all. He can go directly to the numbers because he knows what the factors are, and he just has to do a little bit of algebra. In 3 hours, I think he, I forget the absolute number of excellent numbers he generated. It was several 100,000 on a Raspberry Pi. In Python. The Python implementation is really interesting because they have this module called PrimeFact, which is a generator. And I wish we really had these with Perl, which is you can just ask it for the next thing. Give me the next thing. Give me the next factor. Give me the next factor. And you can delay the computation of the entire problem until you want to get to the next bit. It's like taking a subroutine and pausing it and give you the partial result. And so he used that, and he would do this and figure out these partitions, and I think now the file that has all the excellent numbers that he decided to compute is something like 1.7 gigabytes. And I was really proud that I got like 300 or something like that. 300 numbers, not 300 gigabytes. Okay, so we implement that in Python. And now at the point, as I'm not really doing any computer programming on this stuff anymore, is I've gotten sort of distracted by the proofs in this and looking at patterns in these numbers and all the other fancy things that I never would have thought about if I had stopped at the brute force side. The brute force gets you a short amount of output. You're interested, but you're not really interested. You go off and you look at Twitter or do whatever you do and you don't ever think about it again. But all sorts of other interesting things that started falling out of this. Matthew's Python program just sort of killed the fun because we're not actually looking for excellent numbers anymore. Now we're looking at excellent numbers to do things. But as I'm doing this, even when I'm doing the proofs, and I don't want to pull up a web thing, but maybe I will, since I have a little bit of time. There's also a website called Excellent Numbers, which figures out which phone number to give you. Let's see if I can make this and increase that. And do that. Okay, so I go through all the math. That's no big deal. It doesn't look like it does the LaTeX stuff all that well, but let's go down to. This is a really interesting pattern, and I worked on this for a couple months. And we would have never found this if Matthew had not been able to create these things really quickly. Or maybe we would have, because I had done the 30-digit numbers, but it took me a month. There's a 6-digit number that is 216513. You look at it and, okay, whatever. There's a 12-digit number that is 3201666 and 50133. And then when I start looking at that, okay, we've got this, I don't know how I recognized it at first. I think maybe all these 6s in the middle. So why do all these things have 6s in the middle? Then you realize, oh wait, they all have 2s and 1s and 5s and 1s. You start to realize there's this pattern here. This is a real pain in the butt. I'm going to get rid of this reader thing because I'd rather show you the LaTeX stuff. This is all done in GitHub Pages, by the way, which I'm really pleased with as a way to make web pages. That's okay, there's the auto repetition. See, this is some pretty hairy math. But that's a lot of fun too. That's why I kept working on the problem. Okay, so here's this thing. So I take that pattern and I write it down to the power of 10, and this is what I get. That A is 3 times this rep unit thing, and then a bunch of crap, where n is the number of digits in the number, or in half the number. And then we're going to skip a lot, because we get down to this substitution here, where we got that rep units plus 1 comes into play, and we do that substitution, and all sorts of things fall out in the algebra. And then, look at this. This is the final thing that I come up with, that the b squared minus a squared is 81 times s to the 5th power times the same 3s plus 2. That s being a substitution for that sequence of powers of 10. But let me show you back with that, where did I define s? There it is, s. So 3 times that rep unit thing. But then I come back here, and I get this guy, the 3s plus 2. But what is that? Now remember, that was 3 times the rep units for s. Now I times it by 3 again, so that's 9 times the rep units. Which is 99999, something like that. You add 2 to it, you're back to rep units again. Of the next higher power. Which is a really interesting result when you see that sort of thing in a math formula, that you start off in one power and you end up rep units of another power. So I'm sure there's more things like that. But to figure this stuff out, I was doing a lot of short little stupid Perl programs to make sure I was getting the pattern right. Because writing a pattern that satisfies something like this, and you're off by a couple of ones somewhere, you get really weird algebra happening. So I make those into Perl programs, write it out, make sure I get the right stuff. So anyway, you can read more about this in all the other stuff I did. I have it all here. But what I want to get to is these estimates. If I did it with GMP, it would take 4 years of computer processing time. No, I can divide that by 80 processors though. when Synon did the int 128 stuff, that dropped to 21 days of processing time. And our 36-digit numbers, we did it with 60 years of processing time. Now, again, divide that by 80. If I run that for, whatever, 13, 14 months or something, I get it back. Way past what Mark Chasen ever thought about. And only because I had this interest in, can I take something that I don't even know what's going to happen and work on this sort of thing? And it worked out. I got to learn a lot about C, a lot about GMP, a lot about some languages that I know I never need to use again. And then some Python guy comes in and just kills it. But the reason he was able to do that has nothing to do with the language. He came up with something that was much better that Python facilitated. Okay, anyway, I think we're about at lunch now, so I will stop there. I could talk about this stuff all day because I'm sort of geeky like that, but I think there's pizza coming. I have 5 minutes. I can take some questions, or we can just stop early. If we stop early, we might have time for lightning talks because I have one that's really, really good. Okay, we'll take a break. Thank you.